if the amine has an NH bond, it is capable of hydrogen bonding, right? So with its own molecules. So for example, here we can show some sort of like amine, right? So maybe we'll have, let's do like maybe like this, right? So we have one butane, one butanamine, right? 1, 2, 3, 4, and NH2, right? Like this. So now I'm going to show another molecule of one butanamine, like this. So here we go. We have delta plus and delta plus on H's, delta minus due to the electronegativity differences, right? So between N and H, so the nitrogen will be having the partially negative charge, right? It's more electronegative. So hydrogen is less electronegative. It will have a partially positive charge. That's it. So you have delta plus, delta minus. So and then they will attract electrostatically to make the hydrogen bonding possible between the two amine molecules, right? So turns out that like it was determined experimentally that even though the amines can form hydrogen bonds, so some of them, right, at least. So the boiling points of tertiary amines will be similar to boiling points of alkanes because tertiary amines cannot form hydrogen bonds, right? So then they don't have this like powerful bonding between the molecules. Consequently, it will require relatively low temperatures to boil a tertiary amine, right? So as we can see from the data tables. So secondary and primary amines, due to the fact that they can form hydrogen bonds between themselves, will have substantially higher boiling point temperatures than tertiary amines. So yeah, this is something to keep in mind from this kind of like physical points, physical properties perspective. So in terms of solubility, right? So we previously acknowledged that the amines can form hydrogen bonds. So they can form hydrogen bonds with water, right? So, and we are able to form the hydrogen bonds actually between the primary amines and secondary amines, right, and the water. So we can show it in a specific way, right? So maybe we have some kind of like primary amine. Let's say it's going to be like this one, right? So we have our NH2. This is going to be some sort of alkyl chain, maybe just say like butyl, for example, right? So you can have a butyl here, and then here it is your NH2 piece, right? Primary amine. So then you can form the hydrogen bond between this partial positive H and partially negative oxygen of water, right? So you form the hydrogen bond just like that. So then if you have the secondary amine, you're able to form the hydrogen bond as well. So just switch this to some kind of other alkyl chain, for example, right? Maybe methyl and ethyl now, but still you have this like NH bond that's capable to form the hydrogen bond, right? So now if you have the tertiary amine, so the situation is slightly different, right? So, but you can still form the, you can make it accept the hydrogen bonds, right? So if you have the situation, something similar to that, maybe like various alkyl chains, maybe they're all the same, could be different situations, right? But nevertheless, we have still this delta minus on nitrogen, and then we have delta plus on the hydrogen, right? Of the water molecules. So delta minus, delta plus, and the delta plus again. So as a result, they're able to form the dot, right, which corresponds to the hydrogen bonds, right? So at least in here, so like we have still a hydrogen bond, which is accepted, right? So by the tertiary amine in this diagram. So these are our dots, right? So which signify the bonding. So this is our lone pair, like shown by these like big fat dots. All right. So, great. So now we are moving on to the next thing, which is chemical properties, right? Amines are bases, right? So what does it mean? That they are able to accept a proton, accept H+. So we can show it using a chemical reaction, of course, right? So here we are going to show, let's say, the reaction between some sort of example amine and the example acid, right? So let's just delve into the chemistry, into the chemical reactions right away. So what's going to happen? So let's take a look at what will take place, right? So it can react with water, right? So if we have, for example, let's say here we have one butyl amine with its respective NH bonds, right? So, and then the lone pair here, the lone pair will be able to make the bond, right, between the nitrogen and the H plus, the proton from the water, for example, right? So proton will be donated by the water because water can be can act as an acid. Okay, great. So here you go. This is going to be your proton that will be formed. So then OH minus will be formed as well. And then here we go, right? So this is going to be a reversible process. So because these are like weak base and weak acid, so that will interact with one another and are going to form the respective products, right? So the acid will form the conjugate base, which is going to be OH minus in the situation, and then you are going to form the conjugate acid. So this is base, the base makes the conjugate acid, right? So what's going to happen is that we are going to redraw this, sorry, this is a propyl, one propanamine, right? So that's your propyl chain right here, only 3 carbons, and then you have it here, nitrogen, right? So it's going to be looking like this. So you have original hydrogens, and you have now this hydrogen, which is now here. So that guy, so we'll underscore it. So this lone pair now is shared, and then it is converted into covalent bond. So that's it. So that's going to be, guess what, your conjugate acid, right? So, and then the positive charge will emerge on the nitrogen because nitrogen lost 1 electron when it was making the bond, right, between N and H. So now let's move on to the example of like if it reacts with an acid, for example. So yeah, that's also a possibility. Oops, I have erased way too much. So let's erase, let's turn this into HCl, right? So simplify things a little bit. So if it reacts with HCl, maybe we'll make like a new chain, right? So because why not? So now we have HCl, right, which will react with that. So if you have the acid, so the principle will be the same, right? If you have the acetic, hydrochloric acid, for example, right? So we'll still form this like new bond, right, between N and what used to be H plus, right? So now you're gonna make this new bond, right? And H bond will still be formed, right? So the positive charge will still emerge on our nitrogen atom, right? So very good. So now finally, what else will be left over? Left over will be Cl minus, right? So Cl minus, and then it turns out you can like show it here because it's going to form the salt, right? So between Cl minus and N plus, the ionic bond will emerge. And then this will be kind of a special kind of a salt. It's going to be the ammonium salt, right? So yeah, that's right. So that's going to be the salt of the amine, rather, let's call it this way, right? Because it was derived from the amine and the hydrochloric acid, right? So, and then amine kind of like made the cation essentially, right? Positively charged species. And then the Cl or HCl supplied as a result of this reaction, it supplied the chloride ion. So then you obtain here, in this case, butyl ammonium chloride. So you have butyl here, CH3, CH2, 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 right? So it's almost like butane without one H on the terminal carbon. Now you have like butane with the one hydrogen short, and then you have the butyl. Butyl amine, right? So was your like initial substrate, right? So, or like one butanamine rather, right? So like butyl with the amine, in other words, reacted, right? And then it made the butyl ammonium chloride, right? So butyl here, ammonium, so that is going to be this like NH3 plus combination, and Cl chloride, right? So just like Na plus Cl minus, it is sodium chloride. So here you have a little bit like different name, right? But similar still to sodium chloride. So that, in a sense, the amine reactions.